Question 6, I've got a diprotic acid, H2A. A diprotic acid means that 1 mole of the acid, one of these, reacts with 2 moles of something like sodium hydroxide, which is a base or an alkali, so 1 to 2. That's going to be important later on in my calculation, I'm sure. 25 centimetres cubed of aqueous solution are prepared using 1,300 milligrams of H2A. Remember, you hardly ever use milligrams, you convert it to grams, so I'm going to divide that by 1,000, I feel, and end up with 1.3 grams at some point. A pipette is used to prepare 25 centimetres cubed of 0.112 moles aqueous sodium hydroxide into a conical flask, and then we get a titration. Use the results to calculate the MR of H2A. So, first of all, I can do something with the sodium hydroxide, because I've got 2 values for the sodium hydroxide. Before I start working out titrations results here, I know that a pipette is used to add 25 centimetre cubed, which is 0.025 decimetre cubed, of 0.112 mole decimetre cubed sodium hydroxide. Concentration is 0.112, volume 25 centimetre cubed. Always got to get volume into decimetre cubed for calculations. Concentration is moles divided by volume. Concentration 0.112 is moles divided by 0.025. Multiply both sides by 0.025. I've got the number of moles, 0.0028 of sodium hydroxide. Now that's in the conical flask. The same number of moles, no, that's wrong. Half the number of moles, because it's diprotic acid, it would be the same number of moles of acid would react. But because it's a diprotic acid, 1 mole of diprotic acid react with 2 moles of sodium hydroxide, in other words half the amount. So the number of moles of the diprotic acid neutralized is 0.0028 divided by 2, because 1 acid react with 2 sodium hydroxide. 0.0014 moles of the diprotic acid, this H2A, this fictitious acid, is reacting. Now I come to my results. I've got to look to it for the best 2 results. The best 2 results are called concordant results, and more accurately it means that they're no more than 0.1 centimetre cubed apart. So I'm looking for 2 of the closest here, 2 that are less than 0.1 apart. If you end up with 3, by the way, I use all 3, but I've only got 2. Titration 1, 26.40 and 26.50 from titration 3 are 0.1 apart. 26.75 is 0.25 away from titration 3, and the rough ones much further apart. So I'm going to use titration 1 and 2, and I work out an average. 26.40, 26.50, add the 2 together, divide by the number of results, that's 2, so divide by 2, add them together, divide by 2, 26.45 centimetre cubed is the average from my 2 concordant results. So, I know how many moles I've used to react with the sodium hydroxide, that's 0.0014 moles, and that's in 26.45 centimetre cubed. So, concentration is, I can work out here, I've got 0.0014 moles in 26.45 centimetre cubed, so I can work out by dividing by 26.45 centimetre cubed how many moles there are in 1 centimetre cubed, and then if I multiply by 250, I can work out how many moles that are in the 250 aqueous solution that I started out with. So I'll multiply by 250, 0.0132 moles are in this standard solution that I've made up at the beginning. So in the 250 centimetre cubed, I've now got 0.132 moles. Moles is mass divided by ml, 0.0132 is 1.3 grams. I said I'd have to convert this milligrams into grams at some point, divide by 1,000, 1.3 grams. Rearrange that equation, so MR is 1.3 divided by 0.0132, 98.5 to 3 significant figures. Most of the other values here are to 3 significant figures, so I'm going to go with 98.5, 3 significant figures. The uncertainty in using the pipette is 0.05. Remember, you're taking 2 readings though, so what actually happens is the error is 0.06 per reading. So because I'm taking 2 readings, a start reading, an initial volume and a final volume, I have to multiply by my error by 2, because every time I do a reading, that's the error that could occur. So 0.06 times 2 is 0.12, and then my percentage error is how far out it could be divided by my reading, which is my average of my two concordant results, 0.12 divided by 26.45, multiplied by 100% for a percentage, 0.45%. Before adding the solution, there's a bubble. At the end, there's no bubble. Explain why the air bubble increases the final burette reading. Well, some of it runs into the bubble rather than is dispensed from the burette. So some of it runs into the bubble before it actually starts dispensing. So no wonder you're getting a reading that's higher than expected. During the titration, the student washed the inside of the conical flask with some distilled water. Why is that okay? You'd never wash out the burette. You never wash out the burette because you dilute the solution. That's a standard solution that's in the burette. But you're allowed to wash out. In actual fact, it's good practice to wash anything down the conical flask. As you're swirling it, you should be washing the inside of it with some distilled water, because you're not changing the number of moles in the conical flask. The number of moles of sodium hydroxide is unchanged. Even adding water won't change the number of moles of sodium hydroxide. And so the number of moles of sodium hydroxide stays the same. Therefore, you can work out the number of moles of acid that you're adding, and from its volume and concentration, you can work out the concentration of the acid.